Hello everyone. This is going to be about neural nets. So backpropagation, and we're going to be using NumPy, not Torch or TensorFlow or anything like that. I thought we'd go right back to the beginning. Andrei Karpathy and also CodeMaker King done a brilliant video, and that got me interested. So I'm not trying to copy them. I'm just trying to understand this in my own head, and if this my version of a very simple neural net helps anyone, then so much the better. You've got an input feature of x equals 2. So we're building a one single weight model. Now, real models have billions of weights, but this is just an example of how to get to arrive at one weight. And it's the weight that makes your model work or useful. So 5 is basically our answer, 2 is our input, and we want to train the model to arrive at the right answer. So to do that, it needs the right weight. To work out the weight, it does this. So start with a random weight because we don't know what the weight is, so we have to just put in a random one. We have a learning rate. That's a very thin slice of the, as you can see with the derivative, it's just very, very small. You can make it bigger or smaller, and it'll take your model longer to train, shorter to train, more accurate, less accurate. Epochs is basically a number of iterations that you want to do to arrive at your answer. The Y prediction needs to equal, so it needs to equal the weight times X. So if the X is 2 and the weight is 2.5, Y prediction would be 5, which would equal the actual true value of Y. So to get there, we need to compute the loss, and that's with converting any minus errors to positive, so they can be compared with positive errors, because you're interested in the magnitude of the error, not whether it's below or above the gradient line. So this is a linear. This is like linear regression if you've done that with sklearn, scikit-learn. We're going to be using loss, so the delta of the loss with respect to the Y prediction, the derivative of the loss of the weight with respect to the Y prediction. If you're familiar with calculus, you'll see that that's gone from squared to -2 times, and you can solve that with some maths, which I'm not going to do here. dloss dw, again, that's the chain rule. So this is all kind of calculus stuff. This is applicable for what we're doing here, which is a continuous gradient. If what you're doing is, for instance, a sigmoid curve with a logistic regression instead of linear regression, for instance, then this would be different. So you would need to research that. We do this, and we're checking we're checking what the loss is, and then we apply thin slice times the loss chain rule, which is these two. So it's these two multiplied together, and then we multiply that by the learning rate, then we subtract that from our original weight, and then we keep going. And you can see down here, start off with a random number. We've got 15.99. That's our loss. Sorry, that's our loss with our original random weight, which is 0.822. The second time, it's already getting closer to the answer because we know the answer is 2.5 because do the maths. Third time, closer. Fourth time, closer. And already by the 40, sorry, not the multiples 10 because we did modulo here. So by the 40th, we're down to here. We're at 2.4984. and by the 60th epoch, we are accurate to 4 decimal places. So that is a quick look at a neural net. So this is one weight. And the important thing to remember is that there's millions or billions of weights of the proper model. And then also you would, yeah, you wouldn't be using NumPy. And you get loads of layers as well, and then you start multiplying matrices rather than just a scalar. So this is just a really quick look, and it's just it's nice just to see it happening. So um, cool. It's been a while since I've used Jupyter notebooks, but I wanted to get rid of that answer so we could see it run again. So okay, right, let's run that. And if I do that, it's so quick. You don't even see it run, but how can we make it bigger? I know we could make the learning rate. If we make the learning rate something like 0.01, might actually see something happening this time. You see, that was still quick. I've got a bigger error there. So let's do, rather than let's do 1,000. This is just some quick and dirty experimenting. See, that's quick as well. Like, so, but what you're seeing is that we're arriving at the correct answer quite a while before we complete the code. So actually, so if we make the learning rate, let's go for 0.4. Okay. What I'll do is I'll put this on GitHub and you can experiment with it. So you can see very quickly you get to the answer. So all the, well, we got to it very early there. So this is why it's important to know a bit about how these things get trained, because it's not an exact science and there's always a trade-off between accuracy, time, cost, etc. I'd encourage you to go and watch Andre Carpathy or Codemaker King, who did something on. So this is backpropagation, and it's updating the weight based on the error of the previous attempt. That's how I understand it. So yeah, have fun, enjoy it.